Okay, so if you have read our course outline, you know that next week would be your midterm for this course. And so the lesson on Tuesday would be like a revision. You are strongly recommended to come. We'll talk about the answers for assignment 1. And there are a lot of common mistakes, and our TA would like to talk about them. Okay, so please come. And the second lesson would be your midterm, so it would be in another building, because I need you to sit on every other seats, because now this arrangement is no good. Okay, and you are too close together. So I have reserved 2 rooms for the midterm. It's in Esther Lee building. Yeah, I will send you an email. Okay, so please go to another classroom for the midterm. And I failed to reserve the room for 3:30 to 4:30. So the midterm would be just 1 hour because I can't reserve a room. So it would be much shorter. Okay, you should be happy about this. So just I guess just 3 to 4 questions. That's it. Okay. So because you will not be able to submit your assignment 2 before the midterm, so it will not be covered. The assignment 2 will not be covered in the midterm, okay? But the tutorials will be. So please come to the tutorial, okay? Including this tutorial, okay? So okay, so this lesson would be about risk assessment. So it's like a crash course on studying risk. Okay, so what is risk? Risk is actually probability. Probability of something bad happening to you, or something bad happening to any system, okay, ecosystem. But here in this course, we'll be mainly talking about risk to human beings, okay? So there's some risk in everything we do, okay? So in Cantonese, we say, 行出街都會被車撞死, okay? So what's the probability of that? There will be some probability of that. So this lecture is like a basic idea behind risk, okay? So, since we will all die someday, our lifetime risk of death from all causes would be 1.0 or 100. So we're gonna die anyway, okay? So what's the reasons behind that? So here are the reasons in Hong Kong, right? They have collected all the reasons, okay? First one will be cancer. So 30% of the people die because of cancer. So 1 in 3 of us will have cancer and will die due to cancer, okay? And the second one is pneumonia. So if you're young, you'll be able to get better, so recover from pneumonia. But if you're old, anything can make you weak. And if you're weak, it's very likely that it's a large portion, like 17% of people die from pneumonia just because they are old and weak, okay? And the third one is very popular in the Western countries, diseases of heart. So these 3 together would be a huge amount of population die from these 3, okay? And also there are some brain diseases and other reasons. So following other reasons. So combining all reasons, of course, 100, right? Okay, so these are the data from the year 2015. So I've updated the data so that this is the most updated data, because 2022 is not completed yet. The data from 2022 not completed yet. So this is like the most updated one. They have added another one here, which is from the COVID-19 virus. So 0.1%. So that's why you will not be able to find statistical significance. It's just too small, right? Among the diseases that I've just talked about here. Okay, so cancer, again, around 30%. Okay, so let's get to the actual part where we can do some calculation. Okay, here, this is an example on the risk for people to die from smoking. Okay, how do we calculate that? So first of all, we need to be clear on the unit. There will be no unit for risk because it's a probability. It's like a fraction, right? A fraction with no units. So the second thing we need to clarify before defining a risk would be that if you are talking about lifetime risk, so your lifetime risk of being dead would be 100%. But if you're talking about if you're going to die next year, then it's annual risk, right? It's not 100% definitely, right? And also, if you are focusing on all the people, general public, or just specific group of people. For example, if you're talking about dying from smoking, then you should clarify which group of people you're talking about. And here, this calculation is just for general public, so it's for everyone, including people who are not able to buy cigarettes. Okay, so the estimated death caused by smoking was over 5,000 per year in Hong Kong. The population, I think, is around this year. Okay, 7-point-something million, and probability of death caused by smoking equals to just very, very simple fraction deaths caused by smoking over all deaths. Okay, we have talked about this. How do we calculate all deaths? We use the crude death rate. We can actually check that from the government statistics. You can search that online, just type crude death rate. The crude death rate is giving you a number over 100,000 people here. 10萬人, okay? 係咪10萬啊? 係10萬. Okay, so 600 something people die over 100,000 people. Okay, this is the crude death rate and multiplied by the Hong Kong population, right? Total number of deaths is on the bottom of the fraction. And this one is the estimated death caused by smoking. So it's around 12% that you would die from smoking. Okay, so this is including people who do not smoke and including people who cannot buy cigarettes even. Okay, so it's like a general risk, average risk. So it's just an average risk. Okay, and the risk that a person faces from smoking depends on how much that person smokes. Of course, if you adjust this number to the people who actually smoke, then it should be much higher, right? So clarify which group of people that you want to talk about. So statistically, so this is found from a survey in the year 2000, smoking one cigarette shortened life expectancy by 11 minutes. Actually, in the book, it says 5 minutes because it was published 20 years ago. So now it has become 11 minutes. Okay, so how do they get this 11 minutes? So here are the steps. Okay, so it's very, very simple calculation, but you need to be careful with the meaning behind the numbers. So first of all, we know the life expectancy between smokers and non-smokers. So all these numbers coming from this paper might not be applicable to Hong Kong, but it's like a reference. So they have done survey in the Western countries. So a difference in the life expectancy between people who smoke and people who don't smoke. Okay, it's 6.5 years. So they have collected data from the hospitals. Of course, the doctors would know if their patients smoke or not, right? So they collected the data and do the average. Okay, so this is like average condition. So obtain the average number of cigarettes consumed per week. And they have done this household survey in the year 1996. Okay, so each week, how many cigarettes do the smokers smoke? Okay, do the smoker consume? Okay, and then we calculate the average number of smoked cigarettes in 1 year. Okay, because you already used the unit of year here. So we multiply the number by 52 weeks, and then we get this number. Okay, and of course, we need to calculate the lifetime number of the total number of cigarettes that a person would consume, right? So they also have collected another statistics from the survey. which is the starting age of smoking, is 17, until the death, also an average for the smokers. Okay, they consume a total number. So multiply this 5772 by these years, right? The distance, calculate the time distance between these two. And we would come up for the average number of cigarettes a smoker would have on average. Okay, everything is average in here. So it's an estimation. Okay, so 6.5 years, we turn that into a number of minutes. I just multiply, do the multiplication. And then 5772 smoke for 54 years. That would be 311,688 cigarettes. So we do the very, very simple subtraction, which means that per one cigarette, so this is number of cigarettes, per one cigarette, you will reduce your life expectancy by 11 minutes, not to mention the decrease of life quality at the end of your life, right? So this is an assumption here. Of course, we assume each cigarette makes the same contribution to one's death. Of course, it's not true, right? If your health is deteriorating, then one cigarette would kill you, right? One cigarette would contribute more to your death. But we have the assumption here. Okay, so since we all die someday, we will have to deal with the incremental probabilities of harm. Incremental meaning that if you have different kinds of risks, you should add them together. So I've confused this with another course. In Hong Kong, the Air Quality Health Index, we do the added health risk. The added meaning that you can add the risk together. You can add the percentage together, okay? So that's what it means, incremental risk, okay? So we have to make some connections between the toxic substances with some kind of risk. For example, here is the increase in cancer risk, not death, okay, just cancer. You can get cancer, but you don't necessarily have to die from the cancer, right? So this is talking about getting a certain disease, okay? Cancer risk. For one type of pollution, the outdoor air pollution, they could be carcinogenic, or the things that would cause you cancer, okay? Actually, a lot of the hydrocarbons coming from the cars, they are carcinogenic, okay, or cancer causing, the same meaning for humans, okay? And why actually air pollution is like the among different energy sources, the fossil fuel energy is the one which kill most people, actually, comparing to solar energy and nuclear energy. Surprisingly, you thought that nuclear energy would kill a lot of people, but no, actually the burning fossil fuel would kill a lot of people because of the outdoor air pollution. It contributed to estimated 7 million. What does it mean by premature deaths? Yes, similar to that. So we're gonna die anyway. So if you're gonna die before you're supposed to, that's what we call premature deaths. Okay, maybe if you don't breathe in the polluted air, you can live longer, right? But no, you're exposed to the air pollution and you die before you're supposed to. That's called premature deaths. So this is the estimation. Of course, it's from statistics. Okay. So the risk of some common activities, so to give you some idea, these are not environmental risks for this course. This is just giving you some idea, okay? For example, if you do hang gliding, you will have 1 in 560 of the chance to die, okay? What does it mean? It means that if you go 560 times, there is probability of one of the times you would die, or 560 people go hang gliding, one of them would die. Okay, this is talking about each event, okay? And you can see that skydiving is much safer than this one. I think 2 years ago, a person died doing this in Hong Kong because they have some sudden convection happening and it's not predictable. Okay, and boxing is very dangerous actually comparing to this. This one might be scary, but it's less dangerous comparing to boxing. Okay, and scuba diving, of course, you have some risk of dying. And this one, the car racing is also very dangerous, even though you have a helmet on. Okay, because it's too fast. Okay, so the most dangerous sport on Earth is base jumping. So you're jumping off the building and having a parachute, but you might not open it in time. So 1 in 60 of the people would die. Okay, or if you do 60 times, one of the time you would die. Okay, that's what it means. Okay, and swimming is much safer. Okay, so there are different types of risk. So here we don't have a unit, right? We don't have a unit. It's just telling you one of the times that would happen. Here we have some units in here. So 1 in 6,700 cars. So it's talking about the cars. It's not talking about the people, right? It's not the same. Okay. And here, this one is talking about the risk of dying from taking planes. Okay, if you take a flight, then out of 10,000 flight hours, there would be 1.27 deaths. So you have to fly enough hours to get the risk of dying. Okay. Okay, so in the context of environmental science, we talk about environmental risk. So the things, the toxic things that you're exposed to. So we need to have like a standard. So what's dangerous, what's not dangerous. So you can see that there are different numbers in here. So which one is dangerous, which one is not dangerous. We have like an arbitrary standard. So the arbitrary standard is 1 in a million. So if you have 1 in a million chance of getting, for example, getting cancer from an environmental toxin, then it's considered dangerous, but more than 1 in a million. Okay, so on the left-hand side, we have the activities that increase the mortality risk by 1 in a million, and the risk is on the right-hand side. So you get cancer, you might not die, right? So this is talking about getting different bad things happening to you. Okay, if you smoke 1.4 cigarettes, you will increase over 1 million a chance of getting cancer. So this is all coming from statistics. Or if you fly 6,000 miles by jet, you will get cancer from cosmic radiation. So the radiation activity, if on the plane or on the higher altitude, would be much higher. Okay. What else? Living 2 days in New York or Boston, you get black lung disease. Okay, maybe not very fatal, but still very bad. Okay. So here the examples are not the environmental risk, but I want to show you what does it mean by 1 in a million chance. So for example, if you're talking about dying from boxing, it's larger than 1 over 1 million, right? This is a fraction. So this fraction is larger than this fraction, which means that this activity is unsafe. Okay. And running or jogging is not larger than 1 over 1 million because it's 1 over 1 million, right? It's equal to the acceptable risk. So 1 in 1 million is acceptable. If it's smaller or equal to 1 over 1 million, we consider that safe statistically. Okay. Of course, there's still a chance that you would die from that activity. Okay. So in the context of environmental engineering, we try to control the toxic substances. So if we can control that to a certain level, we will lower the chance of getting some adverse health effects on the right-hand side. So this is what it means. So how do we do that? We control exposure. Maybe we control the emission from the source. Maybe we have the emission elsewhere, away from the people. then we can control the exposure. You don't have to control the emission, you can control the exposure. So if people are not exposed to the toxic substances, then you lower the chance, lower the risks, right? So maybe we install emission control technology, maybe we move away the emission source, or we use newer machines with better energy efficiency, so emit less, right? If you burn less, you emit less. So we have different things to do the control. So we can always go back to live in the Stone Age, right? Stop burning fossil fuel, then everything is solved, but we cannot do that, right? We cannot stop all the economic activities. So, which means that we need to balance between the risk and how much we are going to spend, or the economic price behind having to control the risk, okay? So you can have different scenarios, right? You can stop the economic activity, right? You can stop using cars, you can stop taking flights, then there will be no pollution risk, right? But we cannot do that, right? Or we can stop caring about the risk, and then it will cost us less because we don't care about the emission anymore, but the risk would be high, right, of getting the adverse health effect. We don't want to do that. So what we want to do is in between, right? We control the risk at a certain cost that we are willing to pay, right? Control that we just talked about, right? We control the risk to 1/1 million. So we calculate how much we need to do, right? Do we need to build a wastewater treatment plant to reduce the risk of people drinking unsafe water? Do we need, how much do we need to spend on that? We want to balance these two, okay? So this is just showing you what I have talked about. Okay, here the x-axis is the cost of controlling. Okay, if you go to the right-hand side, more to the right-hand side, higher cost. Okay, and y-axis is the risk, right? Which means that if you are higher in this axis, you have higher chance of getting adverse health effect. Okay, so we need to find a balance. If you are going up on this curve, lower cost, higher risk, right? If you're going down on this line, or this relationship, higher cost, lower risk, right? So we need to find a balance. How do we find a balance? We have a definition of acceptable incremental risk, right? 1 in a million. So if you develop this relationship, you can find the 1 in a million, and you can find the acceptable cost or the acceptable exposure to the pollutant, which means that you can calculate how much you can emit without causing people having higher chance of getting cancer. Okay. So next is some steps of how we can identify the hazard. Okay, so first of all, we need to be clear on the concept that not everyone responds to a toxin in exactly the same way. Okay, maybe today's air quality is really bad, but some of us would be coughing, some of us would not be coughing, right? So we're not robots. We do not respond to the situation exactly in the same way. So if you have a lower emission scenario here, low concentration, and you have counted the number of people who get sick, and you also have counted number of people who don't get sick. Okay, of course there are two groups always. Okay, and if you are in a higher concentration scenario, higher emission scenario, which means higher concentration. Okay, and probably you have more people getting sick. Okay, and less people resistant to the emission, right? So what we are doing is that we are relating the concentration with the number of people who get sick. Of course, if you have a worse air pollution scenario, you will get a larger N1 in here, right? So we need to put that in a graph. So these are the steps that we will take in the context of environmental science. So first of all, we need to do hazard identification. This one, okay. So how do we identify? Of course, you need to identify it. It looks like it's common sense to you, right? Today's weather is bad, or today air quality is bad. You are coughing. So how do you make that connection? It's very obvious to you, but actually, this example would be obvious to you, but there are other examples, right? So we need to determine if the exposure of a chemical is likely to have adverse health effects. So you need to understand where the toxins would be affecting in your body, right? If you're talking about air quality, of course, you're talking about the lungs, right? But nowadays we talk about PM 2.5. So PM 2.5 can penetrate your lungs and go into your circulatory system. So that's why people say that if the air is bad enough, you can get a stroke, because the small particles can go into your bloodstream and go into the brain. So you need to study the path of the pollutants going, or the toxins going into your body. Okay, so a study here is the nature of the adverse effect and the probability of their occurrence. So a toxicant enters the body by different paths. So in the study of environmental science, we need to know which exposure we are talking about. For example, if you're talking about air quality, we're talking about breathing, right? It can go into your body through breathing. Or if you're talking about water quality, if you drink water and the water quality is no good, it's talking about ingestion, right? Food or drink. Or even when you touch some toxicant, it will go through your skin and go into the body, okay? So that's why I would talk to my relatives a lot about this and warn them do not buy any unsafe toys online, okay? Because plastic can be very toxic, actually. Okay, so after entering the body, the toxin can move through your circulatory system. So it goes to different organs that they would not go away. So some of the toxins you can have some mechanism to turn them into other chemicals, but for some of the toxicant you cannot do that. It's just it just stays in your body. Okay, sometimes you will be able to remove them through your different mechanisms in your body. Okay, we have another course for this. It's called toxicology, environmental toxicology. Okay, I'm not going into details. I'm not good in biology. Okay, so there are different parts of our system that would deal with the toxins in our body. For example, liver filters the blood before it's pumped through the lungs. So the toxicants can be in your liver or kidneys, because they are both responsible to filter the blood. Okay. Okay, so we have to identify the hazard. So there are different kinds. So in some ways, we are talking about the time range of the effect of the toxicant. Okay, for the first one, it's called acute toxicity. Of course, it happens really fast. So if you're bitten by a snake, or if you have eaten a very bad mushroom, a toxic mushroom, we're talking about this, the acute toxicity. So it happens really fast. And the second one is mutagenesis, which means that there is some harm to your genetic material. You might pass it to your offsprings, okay? Or it might turn into cancer. So it's not necessarily has to turn into cancer, but it could turn into cancer. So the third one is carcinogenesis. So the toxins which would increase your risk in getting cancer. So there are different exposure to this person, and there will be damage to two kinds, right? The first kind is genetic material. Second kind is other systems. So systems other than genetic materials, which would lead you to have some adverse health effect. Okay, so how do we define toxicity? So here, this table is talking about acute toxicity only, not long-term, right? The second and the third kind, we talk about long-term adverse health effect, right? You don't get cancer immediately if you smoke, right? Just 1 or 2 cigarettes won't kill you, right? So the first one is very urgent, fast responses after single exposure. So organ injury, coma, even death. Okay, so we have the definition is in here. So if you have to eat 15 grams per kilogram of your weight, so I don't know if you are 50 kilogram, then you multiply this by 5 times. If you eat that much of the same thing, then you will get sick. That's the definition of being non-toxic. 所以有一句話咩食飯都會死啊，係嘛？ Okay, even if something very not toxic, not defined as non-toxic, something defined as non-toxic, if you eat that enough, you will get sick. Okay, that's what it means. Okay, this is non-toxic. And of course, if you're talking about the very super toxic stuff, per kilogram of your weight, you just take 5 milligrams, then you get sick. Okay, less than 5 milligrams, you get sick. Then that's defined as super toxic. So I have an example for you, which is K9 in here. It's very, very small amount. Okay, if a person set with 70 kilogram weight, you just need 0.1 gram of K9 to be killed. Okay, lethal dosage. And sucrose is defined as non-toxic because you need to take 1.4 kilogram of sucrose to die from that. Actually, it's not possible, right? If you have to eat that much. Okay, so how do we put that in a graph? Remember that not everyone responds to the toxin the same way. So we counted the people. Okay, so x-axis is the dosage. Dosage meaning the amount of the toxins that we are talking about, milligram per kilogram of your body weight. So if you are 70, multiply the numbers here by 70, right? Is your dosage. Okay, so y-axis here is the percentage of death, okay, mortality rate. So 50%, meaning that 50% of the population die from this toxin. Okay, so LD50, meaning the lethal dosage that will kill 50% of the people. You can see that it's not a linear relationship. At first it's slower, and then it's faster and faster, and then slower again. Okay, so there are 2 kinds of chemicals in this example, chemical A and chemical B. Which one is more toxic? So the LD50 of chemical A is in here. The LD50 of chemical B is in here. So we need smaller amount for chemical A to kill 50% of people, right? On this scale, smaller amount, so more toxic for chemical A. Okay, chemical B, you need more amount, less toxic. Okay. And here, so let's say if you have collected the data, so this is probably from animal testing because you have all the data you need. Okay, so this chemical C has like a different relationship. This is linear, right? We have a straight line in here. So if you are talking about the low dosage and the higher dosage, they do not give you the same kind of response, right? So in the low dosage, which one is more toxic? Chemical A or chemical C? In the low dosage area here, which one is more toxic? A or C? A. Yes, A is more toxic. So if you draw a line from the same mortality rate to the right, and they have different dosage, right? So A needs a smaller dosage to kill the same amount of people. And C, oh, sorry. This one needs smaller amount. So C is more toxic in this region. And this line, A, is less toxic. So C is more toxic in the lower dosage region, the lower dosage region. Okay. And if you draw a line, so if you look at the higher dosage region, draw a line, the same line, and you can see that the LD50 for chemical A is smaller. So A is more toxic in this region. Okay. Okay, so next we talk about the mutagenesis. It's talking about the damage to your genetic materials, namely the DNA that you will pass to your offspring. So there are different kinds of chemicals that would cause that. I will leave that to the toxicology course. Of course, radioactive stuff, the stuff that would ionize the molecules inside your body. If your DNA is ionized, then there will be a chance that you will pass that damaged DNA to your offspring and causing mutations. Okay, lead to malfunctions in cells. Of course, it also can cause effect to you. Okay, the person who is exposed to the genotoxic material. Okay, or you can get cancer. Okay, carcinogenesis. Okay, so we need animal testing to some of the toxins. So here we are talking about some, so we have talked about this acute toxicity. What about the mutagenesis and carcinogenesis? If we talk about these, we talk about long-term exposure, right? You have to be exposed to that toxin long enough, right? So you're talking about very long time, very low probability. Even if we are eating all the bad food, only 30% of the people die from cancer, right? So very low probability. So how do we obtain this low probability? Of course, we cannot do tests on human beings, right? We do tests on the animals. Okay, so if we test 100 rats at a particular dose, very low dosage, we need to wait for the rats to get the cancer. And if we find one tumor, the risk will be 1%. And this will be consistent with the actual risk 0.0 to 3%. Okay. So this is an example. So how do we get, so what we are interested is in this region, the low dosage region and low risk region. And usually we don't get the data in this region because you want the response to be fast. So sometimes we do the high dosage experiment and extrapolate what we know. Okay. And that's why it takes a long time to do this kind of exposure study. Okay, so we can do exposure assessment. What does it mean? So right-hand side here is for human being. Left-hand side here, you can also do this for human being, but most of the times we work with animals. Okay, we use animals to find the dose response assessment. So exposure assessment is that you do survey with specific group of people and obtain the data and then do the statistics. Okay. So human studies, it's very controversial because the response of the animals would not be the same of the response from human beings. So people often challenge that. So a substance cause tumors in mice. Does it cause tumor in human beings? It's not the same, right? And of course, we cannot perform tests on human beings. So that's why we need to do the epidemiology. So it's just statistics. So take a lot of data and then study the relationship. So you need to ask people how much you're taking in, how much of the toxin you're taking in. And of course, you need to obtain the rate at which they are getting sick. And this is very hard because people are exposed to all kinds of toxicants in their lives. So it's very difficult. So disease rates in the real population versus various environmental factors, you need to get a lot of data to do that. We do have a department studying this, is the health department. I think they have a lot of study on this. Okay, so this is like a simple introduction to epidemiology, data analysis. So we need to get the data here. For example, if a person is exposed to a toxicant, then that person, if he gets sick, we would count as this category A with the disease. And some people might not get sick, even though if they're exposed, they're counted as category B in here, even if they're exposed. And of course, there are a group of people who are not exposed and still get sick, which means that for example, some people, they don't smoke, they still get the lung cancer, right? So this is the group of people who are not exposed and still getting sick. So we need to account for the chance of getting a disease without being exposed to that toxicant here. And also, of course, this is as expected, right? If you're not exposed, you should not get the disease, okay? So get the 4 numbers in here. So I have a question for you. What is the path of the exposure in this example here? The path is eating, right? Drinking, eating here, not through the skin, not through breathing. Okay, so we collected the 4 numbers, and then we can calculate, first of all, we calculate the chance of getting sick with the exposure, which is the upper part of this fraction. And then over the bottom part of this fraction would be the chance to get it without the exposure. So imagine the upper part is that you would get lung cancer, the chance of getting lung cancer if you smoke, okay? And the bottom one would be the chance of getting lung cancer if you don't smoke, okay? So we need to calculate the relative risk. So how much of a chance is larger than your background chance of getting some disease? So the bottom one is the chance that you would get it anyway, right? You need to do the division to see how large it is, okay? If they're the same, then it doesn't matter if you're exposed or not. It's not doing anything, right? If they're the same, if it gives you 1, it means that you are getting that disease anyway. Doesn't matter if you're exposed or not, okay? If you have a higher number, higher relative risk, the higher the relative risk, the data is suggesting that it's related to this risk, okay? There are links between exposure and the risk, okay? Or you don't have to do division, you can do subtraction, okay? So the chance of getting lung cancer if you smoke, the chance of getting lung cancer if you don't smoke, no exposure, okay? So if it's 0, which means that they are the same. If they're the same, then it doesn't matter if you're smoking or not. Of course, it's not true, okay? Okay, here is an example showing you some calculation. So after talking to some people working in a plant that manufactures vinyl chloride, which is a type of plastic, it's carcinogenic, and finds out that out of 200 workers, 15 develop lung cancer, okay? And you want to know if it's higher than the background value of getting lung cancer, right? Then a control group consisting individuals with smoking histories, similar to the exposed workers, who are unlikely to have encountered. So if they're not exposed, 24 with liver cancers and 450 did not develop liver cancer. So you need to put down the numbers in the table first, Okay, so exposed to the vinyl chloride here, total number is 200. So if you add them together, it's 200, right? 15 of them get the lung cancer, a liver cancer, and 185 no cancer. Okay, still most of them don't get the cancer, even if they're exposed. So total number is 200. And what about the not exposed group? 450 did not develop liver cancer, and 24 have that cancer. So the chance of being exposed to the vinyl chloride of getting liver cancer would be 0.075. So 7.5% chance that they would get liver cancer, the factory workers. And this one is like the background chance. The background chance would be 0.05. 0.051, 5% chance. Okay, so you will get 1.5 times higher the chance. So if you are careful when you listen to the news, sometimes they will tell you that, okay, if you eat this or if you don't eat this, you get twice as much of the chance of getting some disease. Actually, they're hiding the numbers behind that. They're giving you this one, right? It looks very large, right? 1.5 times more. But actually, the original chance is a very, very small number, right? Only 5% and only 7%. You will have like 2% more of the chance. If I tell you 2% more, you probably don't care, right? But if I tell you that you have 1.5 times more of the chance of getting some disease, you will care about that. So be careful what the news is telling you, okay? They usually tell you this one because it's more attractive of a story, okay? If I tell you 2% more, it's probably you don't care, right? So we calculate the relative risk, and we can do the subtraction and calculate the attributable risk, okay? So this is what I talk about, right? It's 2% more, right? Okay, so there are a lot of limitations in studying the survey coming from the people because we all have different backgrounds, right? Similar smoking history is very, so so these two groups of people, why do we need similar smoking history comparing to the workers in here? They should have similar smoking histories. We don't want a lot of things to be different, right? It's a control experiment, right? We compare the exposed with the not exposed. We want to study the effect of vinyl chloride, not the effect of smoking. So that's why they need to have the similar smoking background. Compare the workers and non-workers. We might need to also care about that. Maybe for the workers, they work a lot and they have worse health, right? Comparing to the non-workers, we don't know that. So there are different things that we have not encountered for. Okay, so we compare the lung cancer rates in the city having high ambient environmental air pollution with the rates in the city having less pollution. So we have to be careful if they're exposed to the same amount of air pollutants. Right, if we compare the two groups of people living in different locations, and if we talk about lung cancer, then that's not good, right? That's not ideal. Okay, so instead we should compare different levels of, so if you talk about the air pollution, sometimes we should talk about the indoor air pollution because most of the times we spend time in indoor quality, okay, which are associated with the field type. So if you cook, okay, inside your house with the real fire, the real stove with the fire, actually they release a lot of hydrocarbons and you cannot tell, okay? They don't have smell. Actually, they stay in your house, okay? That's why I suggest my family to switch to the conduction stove instead of the real stove, okay? Studies may be biased, so be careful which kind of things that could also be changing if you compare with the control group, okay? There may be other reasons. Okay, so the dose response assessment, this one is what we would do with the animals. Okay, so the relationship between received dosage. Of course, if you have higher dosage, you should have higher toxic response, higher chance to get adverse health effects. So this is a suggested relationship. If you have higher dosage, you should have more people getting sick, right? Not necessarily linear, but they should be in a positive changing direction, okay? So the x-axis here is the amount of toxicant being exposed to human, and this is the unit, so be careful of the unit. If you don't put down your unit in your midterm, points will be deducted, okay? Be careful. Okay, milligram of the substance per kilogram of your weight per exposure day, okay? So we have this average over entire lifetime. Okay, and y-axis is just the risk, the probability of getting the unhealthy response. No unit, of course, is the percentage. Okay, the example is 700 cancers in population of 1 million, then you can calculate the percentage here. And if this is a lifetime risk, okay? So if you are calculating any risk, so the risk of getting cancer next year or each year, for example, we have to divide this percentage by 70 years. So this is the average lifespan statistically. Actually, it should be 80 years, but I've used the textbook. They told me to use 70 years. Okay, so it's a very small number getting cancer each year. Okay, so I don't know if you remember this. It happened in Hong Kong, 2015. Lead found in tap water in public housing. Just a reminder that it's untainted water supply from the mains. So from the mains is not contaminated. Actually, the contaminant is coming from the substandard pipes of binding material that release lead, okay? And public housing is developed by Hong Kong government, okay? Those of you who are not local people. So these are the public housing. And the article says there's no consensus on the safe level because it's not supposed to be in drinking water, so there's no safety level. And the government doctor once stated that the average dosage over a lifetime is still low. Why is that person talking about this? Because this is like a common practice that we do. We do the average risk over the whole lifetime, okay? But that's only applicable for chronic toxicity. Okay, if something is really toxic, we should talk about this acute toxicity, which means that we need to go back to the table that we have just talked about. So be careful of which kind of toxicity we're talking about. If you're getting sick within 1 or 2 months, okay, as this is already a very short period of time. Of course, if you're getting sick in a few days, it's definitely an acute toxicity, right? If you eat a bad mushroom, that would be acute toxicity. But if you're getting sick like within a few months, still it's acute toxicity, right? But it's hard to define. Sometimes it's hard to differentiate the two. Like for the chronic toxicity, we are talking about years or decades, right? What about in between? Then it's very hard to define. That's why it's debatable in here. Okay, so there are different types of those response assessment of carcinogenic response. So there are different. So there are 3 different lines in here talking about 3 different chemicals or 3 different toxins in here. So the x-axis again is the dosage. The higher you are, the higher the number you are, you need the higher dosage. Okay, and the y-axis is just the probability of getting cancer. Okay, so the 3 different lines is telling you 3 different stories. Okay, here we have the carcinogenic material, the straight line. So linear response, no threshold, meaning that even if you have 1 molecule of that substance, you will get the risk. So this is what it means. Okay, 1 hit response. Okay, if you have this line, you will start at the threshold, meaning that even if you get this dosage, It's not carcinogenic. So this one is considered as non-carcinogenic. So it needs a very high dosage to lead you to the bad health effect. Okay. And this one is also carcinogenic. You have like a one-hit response also, which means that if you get one molecule of this substance, you'll still get a chance, but this one is with lower comparing to the straight line, right? So probably slower response at lower dosage and then faster response at higher dosage, right? Much higher comparing to this, okay? I'm talking about the slope here, okay? Exposure to any amount of carcinogen creates some risk. So it's talking about the very low amount in here. The curves go through the origin. Yes, this one. Okay. Below the threshold, there's no response from non-carcinogen. Here, this one. Okay. So what we usually do, we expect to do the animal testing really, really quickly. We don't have the time to wait for the effects. So what do? We do the higher dosage to the animals, and then of course it will give you a higher response, right? So we use this data to extrapolate our knowledge to the low dosage area. So that's what it means. Of course, we need to talk about the cost we spend, right, on doing testing. So we don't have the time to wait for the animals at this region. Low dosage, probably all of your animals, if you use low dosage, probably all of your animals won't get the bad health effect and your experiment failed, right? We don't want to do that. So it's hard to get statistically significant results in measuring a risk with very low probability. So we don't do experiments here. We do the experiments here, right? It's very controversial because how do you know if you extrapolate the relationship, it will work in the low dosage relationship? So no model can be, so by model, we are talking about the math model. You do the extrapolation to the lower dosage in here. So it's a choice. So it's a choice by the researcher of the models. Okay, so we have different models here. So the math here is optional. There are two types of model. The first one is like the stricter model, one hit fit to the data, right? So meaning that if you have one molecule of exposure, you will get some chance immediately of getting cancer, okay? And this one is called a multi-stage fit. You can see that at first, you might not get the risk of cancer in the low dosage, and then you get higher and higher chance. So they have different mathematical model. So the so-called model is just a math equation. Okay, you fit the model to the data. Okay, so you have some data points, but you don't have all of them. That's why you need the mathematical model. Okay, so if we blow this part up, it's the range of interest. Why is it the range of interest is in the lower dosage? Because we're talking about the environmental exposure. Most of the times, the higher dosage or the high concentration things would not happen in developed regions. We are living in Hong Kong, it's a developed regions, right? If you're going to a third world country, it might be a different story. But in Hong Kong, if you release something really, really toxic to the environment, it's illegal. So that's why what you can find in the environment is with very, very low dosage. Okay, so very low dosage is the region here, right? Low concentration, the range of interest. So is it toxic if you're exposed to some very low concentration of carcinogens? We don't know, right? So that's why we do the extrapolation to the lower dosage region here. And the two lines here, one is coming from this one hit fit to the data, and the other one here is the multi-fit, which is this one, which means that if you use this one, is a stricter regulation comparing to this one, because you expect the worst, right? This one expect the worst coming from your toxin. We expect one hit of the molecule will increase your risk, right? This one. And we usually use this one. We don't use this one, okay? We use this, and the slope here is called potency factor, the slope. So is the risk of getting something if we are exposed to 1 milligram per kilogram of your weight per day of exposure. Okay, so which means that is the slope. Okay, X is 1, then Y is called the potency factor or the slope of here. It's the same thing. Okay. So for chronic toxicity studies, a low dosage is administered over a significant portion of animals' lifetime. Some of the studies do this, low dosage to the animal, and then they can find out this range. And we have a table showing you the potency factor of different chemicals, actually. So this is explaining more of this potency factor. So potency factor is the slope, and X, and should be Y over X. So Y is the distance here, and X is the chronic daily intake distance here. So that's why it's the risk per 1 kilogram per day, or per 1 milligram of your toxin per kilogram of your weight per day of exposure. Okay, so it's called chronic daily intake, CDI. You will need to calculate this a lot. Okay, so if you're given the slope, so it's a reference value from a table, and if you calculate the CDI, chronic daily intake, which means that if you know that person, how much of that person is exposed to that toxin, you multiply by the potency factor, you will get the lifetime risk. You can calculate that. And you know that if this CDI is acceptable or not, because you need this to be lower than 1 over 1 million. Okay. Oh, okay. I think, okay, maybe let's take a break for 10 minutes, okay? Okay, let's continue. So we have, I think I should go to the table of, yes, this one is the potency factor of different toxicants in here. So we have, which one we have talked about? I think we haven't talked about any one of them. But for each of them, there will be 2 potency factors. The first one is the oral route. The other one is inhalation route, which means that they should have different standard in terms of the pathway, right? If you drink it or if you eat that, this is the potency factor. And if you breathe that, this is the potency factor, which means the slope is not the same in the graph, right? The slope for this one is much higher. Okay, which means that the lower dosage will lead to a higher response, right? So be careful which path that we're talking about. Okay, so how do we make use of the potency factor? The potency factor is like a reference, which means that if you're asked if the question is giving you the exposure, you can calculate the risk, right? And you know if that concentration is bad for you, right? If your CDI is too high, then your incremental lifetime risk is higher. If it's higher than 1 over 1 million, it's unsafe, right? So this is how we make use of this equation. So to put the risk on one side, then it's CDI, chronic daily intake, times the potency factor, the slope. Okay, so how do we calculate the chronic daily intake? That's a little bit more complicated. It's milligram per kilogram of your weight per day. So if we separate this term into a fraction, it would be the average daily dosage per your body weight. So the average daily dosage is milligram per day. So the total lifetime dose average over 70 years of lifetime. So you have to calculate this. So do we have an example? Yes, we have an example here, but I would like to take a detour to talk about this. We have some local data. For example, this is the so-called Environmental Impact Assessment Report, EIA report on building. So they have to do this report before they started to build this third runway in the Hong Kong airport. Is the assessment of this construction on the contaminations of land, water, and air. So in other words, they can pollute the environment, but they cannot exceed what the law is requiring them. So you can only pollute the environment to a certain level where the law is allowed. The law is allowing you to. Okay. Okay, so this is an example of having chloroform, really bad thing, in our drinking water. Okay, so when drinking water is disinfected with chlorine, so you want to kill the microorganism inside and you use chlorine, but there is a byproduct which is undesirable. The byproduct is chloroform here, CHCl3, and it could be formed, okay? And suppose a 70 kilogram person drinks 2 liters of water per day for 70 years, and we have a very low concentration in that drinking water. So find the upper bound cancer risk. So just find the cancer risk from the potency factor. Why is it called upper bound? So it's the highest risk that you can get because we have taken the stricter model in here, right? The stricter model, which is this one, is giving you higher lifetime risk than this other model. So this is like the upper bound high lifetime risk that we would get something. So the upper bound cancer risk for this individual using the potency factor provided in the slide. So in the slide from the table, you choose the chemical chloroform and then find the potency factor. Here is talking about drinking. So take this oral route. Don't take the inhalation route. Okay. Maybe we go through part A first. Okay. So we calculate the chronic daily intake, average daily dose per body weight. Okay, per unit of body weight. So you have this concentration. This is the concentration in your water, and that person takes 2 liters of water per day. Okay, and we assume that this person drinks this much of water every single day in his life. It's like an average. Okay, multiply that and you will get the chronic daily intake. This is small amount, right? Per kilogram of his body weight per day. Okay, and if you find this chronic daily intake, which is supposed to be representing the exposure, okay, if you have the exposure, you can calculate the corresponding risk from the potency factor, right? This is the slope potency factor, relating the two things with the slope. Okay, now you can calculate the risk coming from this chronic daily intake. So the risk equals to chronic daily intake times the slope times the potency factor. You can check that from the table. It's 6.1 times 10 to the power of minus 3. Okay, multiply them and then you get 17.4 over 1 million, which is bad because the acceptable risk is 1 over 1 million. So it's 17 times more than the acceptable risk. Okay, so this concentration is not acceptable. Okay, so pretty straightforward calculation. So part B of the question, if a city with 500,000 people in it also drinks the amount of this water, how many extra cancers? So we can calculate that from the statistics. From the population, this one is the population, we have the rate or the chance of people getting cancer. And they're talking about the annual risk per year, right? So the lifetime risk have to be divided by 70 years. So only 0.12 extra cancers you will get from drinking this chloroform per year, which means that is not detectable because you can see the scale here, right? 31%. If you check the table, the smallest one would be like 4 or 3%. If it's 0.1%, then is not detectable, even though the risk is not acceptable here. If you check the number of people who die, then it's not detectable. Okay. Part C I've already covered. Okay. So the other part of the question is asking you the other way around. So if that's not acceptable, what is the acceptable concentration in our drinking water, right? How much do we need to lower the risk, right? We need to spend money on the water treatment in order to lower the concentration. Maybe we cannot get rid of the chloroform altogether, but we can reduce the concentration. So which concentration we need to reduce to? How do we calculate that? We use the acceptable risk, right? We accept 1 over 1 million people getting cancer, right? So which means that we can use the potency factor and calculate the chronic daily intake in the reverse way, right? In the last question, we used CDI to calculate the risk. Now we use the risk to calculate the CDI, just the same equation, okay? So CDI equals to the average daily dosage. So we separate the CDI into different terms, the chronic daily intake into concentration and water intake every single day and body weight of that person. So we don't know the concentration here. We want to find out, okay? 2 liter drinking water per day, 70 kilogram of the average weight per person. Okay, so we are going backward. Okay, we are having acceptable risk, and then we want to find a safe CDI. Okay, and we have the CDI here, and we can put it back to the equation, right? CDI is this one. C is not known, but risk is known, right? It's 1 over 1 million potency factor from the table, just one unknown here, which is the concentration C. Okay, we can calculate that. So per liter of drinking water, only 6 microgram of chloroform, 6 to the power of -3. Okay, 6 times 10 to the power of -3 milligram per liter will give you the acceptable per pound risk, 1 over 1 million. So the question is either giving you the concentration or giving you the risk. So you need to know which one that you're calculating. Okay, so next is a little bit more complicated because this time the exposures is less than a lifetime. It's not like drinking water in a city. Okay, so this time we need to find out the total intake divided by the weight and divided by 70 years. So this is just explaining the different situations. So what we just talked about is the lifetime exposure, right? The exposure throughout your whole lifetime. And in the next section, we only talk about this intermittent exposure. So you're exposed to, probably you're working under in a certain factory for 20 years, and that's your period of exposure. So we only calculate that. So in the previous sections, we talk about this, right? Average daily dosage throughout your whole life. And if your exposure is less than a lifetime, it's just a certain period of time, you need to calculate the total intake here. Total intake for this period only. Okay, so milligram per unit weight. And then you need to spread out your intake over your whole lifetime. So the concentration is reduced to a very small value, right? The CDI, because it's average, even though you're exposed to the toxicant for only, for example, 10, 20 years, you will need to divide that with your whole lifetime in here. Okay, so this is the equation to calculate that if your intake is less than a lifetime, the exposure is less than a lifetime. So if the contaminant is in drinking water, the CDI, chronic daily intake, is expressed as, of course, the concentration, right, of the toxicant in the water per unit volume of water times the intake times the exposure. So if you're exposed to, for example, 2 months of your life, then you calculate 60 days per life, right? And here, intake during that period, how much you're drinking the water. So this is talking about the water. This is talking about the concentration in the water. And the bottom part of this fraction is just the same. Okay, so you are calculating the total intake on the upper part of this fraction. And for the air pollutants, things that you're breathing in, we use a different unit in the volume, cubic meter. So it's just exactly the same, but the volume here is changed to cubic meter. Intake also cubic meter, you're breathing in a lot of air each day, and also how many days you're exposed during your lifetime. Okay, and the bottom part is just the same. So similar expressions can be used for contaminated food or soil. So here is an example. So we need to estimate the incremental cancer risk for a 60-kilogram worker exposed to particular carcinogen under the following circumstances. So the exposure time is 5 days per week. Probably you only work 5 days. Okay, 5 working days per week. Okay, and 50 weeks per year, you take some time off or you take vacations for 2 weeks, then just 50 years of working days over 25 years of time. So this is practically a lifelong career path, 25 years for the same job. Okay, so the worker is assumed to breathe in 20 cubic meter of air per day. The carcinogen has a potency factor of this one. I think it's -1 in here. Okay, and its average concentration. So it's giving you an average concentration per unit volume of air. Okay, so calculate the chronic daily intake first. Concentration, which is 0.05. Intake rate of air. So breathing in 20 cubic meter of air per day. And because you work 5 days a week, 50 days per year, and 25 years per lifetime. So these 3 terms here together, they will become your exposure numbers. So we're giving you these information so that you can calculate the total number of exposure, right? 5 times 50, 50 times 25, total number of days. Okay, and divided by body weight and 70 years. So this is like the standard age that we have. So the average weight, age of people times number of days per year. Okay. Okay, and then we have found the CDI, chronic daily intake. Of course, if we have the chronic daily intake, we can use the slope to find the risk. So the risk of getting cancer from this chemical is 81 per 1 million, which is 81 times more than the safety value, which is not good, not ideal. Okay, so here is an example of talking about benzene is carcinogenic. So let's say some industrial factory facility emits benzene, and your village is exposed to this benzene. So the atmosphere is moving the benzene from one place to another. So air quality models predict that 60% of the time, the prevailing winds blow the benzene away from the neighborhood. So away from the neighborhood. For 40% of the time, benzene concentration will be very high. Okay, 0.01 milligram per cubic meter. So use the standard exposure factors from the table. So it's talking about potency factors to assess the incremental risk, which means that you need to find out the CDI, right? The chronic daily intake. They're asking you for the risk, so you have to calculate the chronic daily intake and then use the potency factor to find the risk. If the facility is allowed to build, if the acceptable risk is okay. So find out the exposure factor from the table first. So this is a table that will be given to you in your midterm, okay? EPA exposure factors recommended for risk assessment. So how do we read this table? So first column is called the land use. So where you're talking about. Is it talking about people where people live, residential area or industrial commercial area? So if you work in a factory, probably you need this, right? Or if you work in a farm, you need this, okay? So because this is talking about residential area, so we need this land use. Okay, exposure pathway, just like what I had asked. So you need to know which pathway is going into your body, right? If you're drinking the water, if you're touching the soil or dust, or if you are breathing in the contaminants. So inhalation is breathing in the contaminants. This time is talking about breathing in air. So we need this, the red box. Okay, so the daily intake for adult, we breathe in around 20 cubic meter of air every single day. And this one is the reference exposure. Let's say you take 2 weeks off from, maybe you go traveling, maybe you go visit your family, right? Sometimes you don't stay in the same place. So this is the average time you stay in the same city, right? 350 days. And so this is an estimation of how people move around, right? We live in the same city for 30 years. So this is what it means. The average number of years that people live in the same location, okay? And the average weight of people, of adults, okay? So we calculate the chronic daily intake first. Concentration is given to you by the question 0.01 milligram per cubic meter of air. And 20 cubic meter per day, you find this from the table here, 20 cubic meter daily intake, right? So they didn't put down per day, but it's in the column here, in the column title in here, daily intake. Okay, 20 cubic meter per day and 350 days per year times 30 years. It's guessing how much time you're staying in the same place. So it's from statistics, 350 days per year that you stay in the same city and you live in the same city for 30 years. So putting in different numbers in here. So body weight, average 70 kilogram, 70 years of lifespan, and 365 years per days per year. Okay, and so only 40% of the time that the wind will blow the benzene to you, which means that you need to reduce the chance by 40%. So for other 60% of time, the wind is blowing your benzene away. So reduce the chance by 40%, which means that this is the concentration. This is the chronic daily intake you will get every day. Okay, and then you plug that into the equation. So pretty simple equation. Times the potency factor. Check that from the table, benzene. Where is it from the table? Here, benzene. Okay, and you are talking about inhalation, which is this one. They are the same actually, but you have to check this column. If you're talking about breathing, you're talking about drinking, this column. Okay, 2.9. Yeah, 2.9 times 10 to the power minus 2. Okay, do the product of them, and then you find out that 13 people out of 1 million people would get cancer because of the concentration, which is not acceptable. It's 13 times higher than acceptable risk. Okay, so if the question is asking you the other way around, which is the acceptable concentration, what do? You put in 10 to the power of minus 6 in the risk, and then you calculate the concentration. The concentration here is no longer 0.01. This is the reality, right? What's the acceptable concentration in the environment that would give you 1 over 1 million people getting sick, okay? calculate the concentration back. Okay. So I know there are a number of days on the top of this fraction and on the bottom of this fraction, but they mean different things. On top, they're talking about your average stay in a city. On the top is talking about lifetime total number of days. Okay. Okay. Maybe we talk about this next time. Okay, let's talk about this next time. Just a few slides left. Okay. Any questions? Okay, if not, then you can leave. Thank you.